Now we're going to take a look at geometric series, specifically a finite geometric series. Remember in the last video I told you that in calculus you'll be learning about infinite series, where they go on forever. But in this class we're just going to focus on finite series, where there's a definite beginning and an end, a starting and a stopping point to the series. This phrase, finite series, is also interchangeable with partial sum. You can use one or the other, but they mean the exact same thing. So let's take a look at the very first problem. It says, write the partial sum of the first 5 terms of the above sequence in sigma notation. So sigma notation is going to be what we see here on the left side of the equal sign. So let's go ahead and start writing. So we have sigma, and then we're going to say that we're starting from the very first term in the sequence, and we're going to continue to add and add and add, and then finally stop when we get to the 5th term. And then if you recall, what goes right in front of the sigma, this part right here, that is the explicit formula. And since this is a geometric series, we need to know what the explicit formula is for a geometric sequence. So if you recall, the formula is going to look like this. So a sub n equals the first term in the sequence multiplied by the common ratio, and all of that is to the power of n minus 1, right? So this part right here is going to go right in front of sigma. So let's start by finding the first term. So in a sequence, the first term is 3. What's the common ratio? Well, to get from one term to the next, it looks like the only thing that we're doing is multiplying by 2. So that is our common ratio, is positive 2. And then the last thing is, the letter that I'm using here, n, just has to be the same letter as what I'm using for the index. So I have to change this n to an I. So this is to the power of I minus 1. All right, so now I've written this in sigma notation, and then the right side of the equal sign, so all of this right here, is what we're going to use to evaluate this, okay, or to figure out what this equals. So this formula, it's different than an arithmetic series, and I actually think it's a lot easier to use than the arithmetic one. I don't have to find the last term in the sequence. All I need is the first term, the common ratio, and then n, okay? So let's start by plugging that into this formula. So the very first term in the sequence that goes in the numerator of this fraction, that is 3, okay? That's going to be multiplied by 1 minus the common ratio, which we said was 2 a minute ago. And notice that the n is the same n that's sitting here on top of sigma, okay? So it's going to be raised to the power of positive 5. And then in the denominator, I have 1 minus 2. So now if you plug this into Desmos or your calculator and figure out what this is, we should get the total sum. So I'm going to do 2 to the power of 5, all of that minus 1, multiplied by 3, and then divided by negative 1. Okay, so I am getting a total sum of 93, okay? And that makes sense, because if I was to look at this sequence, and if I was to add the first 5 terms, right, I would be adding 3 plus 6 plus 12 plus 24 plus 48. And if you plug all of that into your calculator and add those all up together, I definitely get 93, okay? So calculating this using this formula and putting it in sigma notation, I did all of this correctly. I got 93, so that totally worked. All right, so now let's try this with a little bit different of a problem. So now I have to sum 45 terms, and this is the sequence that I'm using. So let's start first by writing this in sigma notation. Remember, you can use any letter that you want for your index, so let's use an X just because, okay? So I'm starting from the first term, and I'll add until I get to the 45th, and that's where I'll stop. And then now I need the explicit formula in front of that. So using the geometric explicit formula, I'll put negative 3 as my first term. And then the common ratio, well, to get from one term to the next, it looks like I'm just multiplying by -1. Okay? So -1 is going to be what r is. Okay? And then all of that is to the power of, and we're using the same letter as the index, that's to the power of x minus 1. All right, so there's everything in sigma notation. And then now I'll use the formula that is in this box up here in red to evaluate that sum. So I'm going to do the very first term, which was -3, multiplied by 1 minus -1, that was the r, and then that's to the power of 45, all over 1 minus -1. All right, and then into the calculator, all of that goes. Please make sure that you are using all of the parentheses, especially the parentheses around the -1 here when you raise it to the power 45, or else you're going to get a different answer, okay? So make sure you include all of those parentheses. So, 2 for all of this turns to 2. 2 times -3, well, that makes -6 in the numerator. And then in the denominator, I get a +2. So that is going to simplify to -3. So that would be the sum, the total sum, if I added all of the first 45 terms together. I get -3. All right, the next two finite series we'll be looking at don't have sequences written out. Okay, where these last two, we had a sequence to refer to. Here it's only written in sigma notation. Thankfully, we have all the information that we need, though, to plug into this formula to calculate the sum, okay? So for that formula, the first thing I need is the first term of the sequence. Well, recall, since this is the explicit formula, the number that's sitting right out in front of the parentheses, this is the first term in the sequence, okay? So your first term is -4, and that's being multiplied by 1 minus, and then what's the common ratio? Well, that's the number that's in the parentheses here, so this is your r. And then lastly, the n, that's whatever number is sitting right on top of the sigma. So the n is 7. And then all of that is over 1 minus r again, so 1 minus 2. Okay, and then now let's evaluate all of that. So I get 2 to the power of 7, 1 minus all of that, times -4, and then divided by -1. I am getting -508. Okay, so that's the total sum. If I evaluate this finite series, is -508. All right, we'll do this one more time for this finite series. Notice here that I don't have a number in front of the parentheses here. So I don't see a number right there for my first term in the sequence. So if you don't see a number, then what's your first term? So if you're thinking that the first term is 1, you're totally correct, okay? So that first term in the sequence is just a +1. If we don't see a number there, then it's +1. All right, so that's the first term, and then I have 1 minus the common ratio, and that's this 1/4 right here inside the parentheses. I'm going to change that to a decimal, so that'll be 0.25. And then that is to the power of 12. And that is all over 1 minus 0.25. Okay, so if we calculate that, I am getting a value of 1.333. It repeats for a while, and then I get 254 after that. So I'm just going to round this to the nearest tenth. So 1.3 rounded to the nearest tenth, that would be the total sum for that series. All right, and then the very last thing I want to show you in this video is when we just consider how to use each of these finite series. So we have our formulas that we learned for the arithmetic and our geometric one that we learned right now that helps us calculate this, okay? But again, I want to take a look at what these series are doing in slow motion, okay? So what this is actually doing right now is it's saying that I'm starting from the first term, right? Meaning that I'm taking 1, and then I'm going to plug that in for this k that's right here. All right, so let's start doing that right now and try it out. So if I plug 1 in, then I'm going to get 0, and that'll be 3 times 2 to the power of 0. Well, we know that anything to the power of 0, that just turns into 1. So all of this right here becomes 1, and then 3 times 1 is just 3. So this is saying that our first term in the sequence is 3, which completely makes sense because that's the number that I see here in front of the parentheses, and I know that that's the first term in the sequence. Cool. So then the next thing that we would be doing is going to the next number that we're indexing. So we've already plugged in 1, so now we're going to plug in 2. So if we take 2, plug that in for k, well then I get 2 minus 1, that's 1. 2 to the power of 1 just stays as 2, and then 3 times 2 is 6. So 6 is the second term in the sequence. And remember, this is a sum, so that means that I'm adding these numbers. So 3 plus 6. And then now I'll go to the next index. So now I'm going to plug in 3. Plug in 3. 3 minus 1 is 2 to the power of 2 is 4. 4 times 3 is 12. So 12 is the next term in the sequence. So if you're seeing the pattern here, because the common ratio, the r, is 2, like it makes sense, I'm just multiplying by 2 to get from one term to the next. So I'm betting if I plug in 4, right, if I should probably get 24 that comes out next. And we can test that by plugging it in, right, like we plug in 4, that gives us 3, 2 to the power of 3 is 8, 8 times 3 is 24. Okay, and then lastly, I'm going to plug in 5, and then right after I plug in 5, that's where I stop, okay? And we should get out a total, once we plug in 5, of 48, okay? So that's what this is doing in slow motion. It's telling me I need to add all the numbers in this sequence all together, and what's that total sum? And I would get that answer if I added all these numbers together, okay? Before we actually calculate that, I want us to now take a look at the next finite series, okay? So same thing, let's just start plugging in our index. Notice there's a couple things that are different here, right? Like I'm starting at 0 now and I'm ending at 4. So let's just see what happens, okay? So let's say I plug in 0 in for k. Well, I just get 3 times 2 to the power of 0, which I just had a second ago, so we know that that turns into 3, right? And then we go to the next number, so I should be plugging in 1 now. Well, that just makes this all turn to 6. And if I plug in 2, well, that gives me 12. So it looks like I'm getting the exact same series here. So I plugged in 3, 6, then I got 12. I plugged in 3, I'm going to get 24. And then finally, if I plug in 4, I get 48. Well, okay, what's happening here? This one stopped at 4 and this one stopped at 5. Why do we have the same amount of numbers here? Okay, let's really carefully look at our indexing. So I started with an index of 1, then 2, 3, 4, 5. I had 5 numbers that came out. Here I started at 0, so check this out, 0, 1, 2, 3, 4. Okay, so because I started at 0, now I got a result of 5 numbers instead of 4. If I started at 1, then I would have got 4 numbers, but because I went back a step and started at 0, I actually got the same output as this last series, okay? So I just want to show you that just in case you see some series that start at 0 instead. You can plug them in the same way, and get, for this one, a sum that looks like this, okay? Finally, let's take a look at the very last one here. So if we continue to do the same thing that we're doing, take 1, plug it in there, we get 3 over 2 multiplied by 2 to the power of 1. Well, that's just 2, and those 2's cancel out, so I just get 3 for the very first term in the sequence. And then if I plug in 2, well, 2 to the power of 2, that makes 4, so, well, when I simplify that, that just multiplies to make 6. So you might be seeing what's happening here, right? Like, I'm going to get the exact same series that I've been getting for these last 2. And you can plug it in the rest of the way, and you will get the rest of these terms that result. So this is just a kind of a cool way to show you can write your series 3 different ways and still get the same numbers that you're adding together, okay?